Thanks for the nice introduction. I'm Anthony. So as you know, I'm not really fully working on this area. I'm really actually from the other side of quantum computing. That's where I mostly work. But I guess I'll tell you something about random matrix theory. And I guess really thankful to have worked with these awesome random matrix people. I guess Jorge, Joel, and Ramon, who told me about this random matrix stuff. Okay. So please interrupt me anytime. And I also want to give you an impression that this talk might be very different from other ones you might have seen in these days. Because I think I'll try to give you like a very baby derivation of this by working through like very explicit examples. Okay? And hopefully you get a gist of this argument, and then so you can envision how this could apply in a more broader setting. Okay. Okay, let's get started. So here's like a very vague setting where you're given this nice random matrix families. Pick your favorite ones. It could be unitary or Hermitian. It could be kind of sparse. Pick your favorite one. I guess here we're kind of interested in the dimension n. Right? That's kind of the only parameter in the problem. And we want to start with a very, very generic question. So it's probably not precise enough for doing math, but I want to just ask, how do we, when someone gives you this, if you're a grad student, your PI told you to do some computation for some expression, it could be some moments, some norms, or some tensor products, how do you go about this problem? At least, this is kind of how I view this question, because because for me, a lot of my life is just applying random matrices to quantum. So in that case, it's really just, oh, hey, here's an expression you need to calculate. If you calculate, you win. And then you might need to invoke some Weingarten. Get your favorite Gaussian integration formula, and then if you grind through 30 pages of calculation, you kind of get some results, and you win. Don't kind of care so much about kind of the deep reason why all this works. Okay, but in this setting, I'm just kind of find this very frustrating. Each time you have to do some very long calculation. So it's just somehow like a nice way to do this, right? That would somehow handle all these different ones. Okay. So I guess for moments, this sense might be a bit simpler because I guess you kind of know what it should do. There's some weak convergence guarantee that you kind of already know when n is infinite, it should do something, right? It should converge to some nice objects. Okay? But but for moments, if you want to make it more quantitative, right? You want to know how it depends on n, and both p and n, it becomes probably still doable. Becomes slightly more involved. Okay? And for norms, I believe this is not always trivial. And then each time you do this, kind of pay a big effort and write a long paper. And I guess these tensor product kinds of want to explore what will happen if you try to enlarge the dimension so that it's much bigger than n, right? So for example, if A is super, super large, it could be much bigger than this dimension n. And I guess this case is when matrices could have correlation with other ones. So this kind of gives you like a somewhat representative list, at least for the matrices that I would personally encounter. Okay? So how do we go about this, right? So in such a general setting. Okay, so here's kind of the high-level claim, is that low-degree properties of large random matrices can be controlled by some leading order 1 over n expansion. Okay, so low degree, you should think of as just try to capture what we have just seen in the left side. And this 1 over n expansion is, I don't know if people use this term here in this community, but this kind of thing is very well used in physics. So you kind of just say, okay, I want to organize my thing in terms of 1 over n. And there's some kind of a heuristic way that you could do that. Okay. And so I'm going to try to support this theme by giving you one example calculation, and hopefully that would generalize. Okay. So here's going to be the setup. So I will kindly ask you, all the expert, to forget everything you know about GUE. Okay. But this is some ensemble, and then here's the normalization. So supposedly you should somehow have norm 2, but you actually don't know that. So okay. And then instead, I want you to only assume these sort of more coarse-grained properties about this matrix. Okay? So first, somehow you're given this kind of crude moment bounds. It ends up telling you that there's like a priori bound on roughly how big it could be. So in particular, this k would just be 100, something that's not 2. Okay, so you somehow don't exactly know where the spectrum is. And then second, you're given that someone told you that when n is infinite, it converges to something nice. Okay. And also, you're aware that there's existence of a somewhat mysterious 1 over n expansion. Okay, so somehow you don't exactly know what this polynomial is, but it can be organized into some low-degree polynomial in 1 over n. So right now, you may feel this setting is very artificial. Why these set of assumptions? So the first reason is this is what I know. Currently, I know. Okay, so I guess that the true reason is that somehow this, each of them actually plays a role in sort of the argument, and you can see that this is somehow the more or less, almost the set of minimal assumption you need to kind of do the current argument. And there you kind of somehow like if you have another random matrix ensemble that's more complicated, somehow these three kind of holds in sort of once you tweak it in sufficiently. Okay? So this is a minimal assumption that we'll only assume.
Sorry, for this assumption on the norm.
Yeah.
K is just a fixed constant that's
not 2. Yeah.
So some fixed large constant that's.
Yeah, I guess you could get this from epsilon nets. So for now, just assume this is true, and it would have some role in the argument.
And presumably C is negative.
Yes. yes. Thanks. Yeah. Okay. So I'll start with a very baby example that hopefully doesn't fully mislead you. So let's just try to do some spectral, try to capture some spectral property, right? So here, I guess you could really place your favorite test function, but this one is just one of them. This e to the IGT kind of is like a Fourier transform. So you would guess that it better be very close to a semicircle if n is really infinite, right? That's one of the assumptions we have. However, if you kind of want the n dependence, you cannot get this kind of nasty-looking series expansion, right? And a priori, it's not really clear what these guys are doing, right? Are they growing exponentially with t? Are they bounded? A priori, it's not very clear. Right? All you know is that there's like some way to organize it into 1 over n. Who knows whether this series makes sense or not? Okay. Well, it does work if t is fixed and n is infinite, right? Because this is just convergence to the semicircle. Okay. So the question is, is there any way that we can get holds on these higher order terms without just basically doing the whole problem, right? Without explicitly getting all the combinatorics underlying this, right? So you see, the difficulty in doing this combinatorics is that there's like some imaginary things here. Like these things are oscillating very, very badly. So like if you don't do it so very carefully, you can get something growing very quickly with t. Okay, so how do we do this, right? Okay, so somehow there's like a very magical thing that we will use is a basic inequality about polynomials. So there's a very, very long, very old result. So it says that if you have a polynomial, it's low degree and bounded, it couldn't sort of oscillate too badly. So it has small derivative. Right, suppose degree is p. Then if you pick an interval, then its derivatives must be bounded by 2p squared times of its maximum. Right? In some sense, this is telling you that a low-degree polynomial, if you confine it to just kind of 1-by-1 box, it couldn't oscillate too badly. Right? This is pretty intuitive, and somehow this sort of the quantitative bound is 2p squared. Okay, and then so here's one example where degrees, I think it's 7. But it's like I guess if you shift the 7th Chebyshev polynomial, it kind of looks like a sine wave. And I guess, when you get very close to the edges, the derivative starts getting bad. Okay? And somehow this Chebyshev is kind of what saturates this bound. So around here is exactly 2p squared. Okay? Right? You can play around with this bound. So you can say, what if I don't use this oscillating polynomial? I use like x to the p. And if you go through this, you realize it doesn't saturate this bound. Right? So if it's just x to the p, if the derivatives is just p times x to the p minus 1. Right? So the factor is p. Right? If x is between 1 and 0. Right? So there's really nothing crazy going on here. Okay? Any questions?
Is it hard to prove this inequality, or is it something?
Oh, okay. I don't know how to prove this, but it was proven a long time ago. So. Yeah.
There's an easy.
For the first derivative, there's an easy proof.
Yeah.
Yeah, I guess there are also higher order versions of this. Maybe, yeah, there's higher order versions of this, and there also, I think, today I think there are lots of variants of this that captures slightly different families. It could be rational. Yeah, in many ways you can kind of tweak this, but this is kind of the most sort of the starting, the most baby version. Okay, so let me also just tell you, this whole thing kind of originally came from some weird thing in the quantum query complexity. That I don't think you guys would ever seen this, but there somehow this also played like a magical rule that you say, oh, I want to study quantum algorithm. It's so hard to study general quantum algorithm, but quantum algorithm somehow its behavior has to be a polynomial in some variable, and then somehow you invoke this, and then the proof is done. So this this polynomial method always have like a magical flavor to it. Okay, so let's try to plug this into our random matrix analysis. So the observation is that quite often random matrix quantity are low degree. If not exactly low degree, often approximately low degree. And let's just try to plug in the Markov inequality with this suggestive variable, x equal to 1 over n. Okay. So assume your function is exactly degree p. Then you can do calculus, right? So f of 0 minus f of x is bounded by the derivative along the interval. Very humble. And then you bound the derivative by Markov, right? So there shouldn't be any surprise here. This is really basic. Okay. But I would like to show this figure because this 1 over n actually fits very nicely in this box, right? So this is 1 over 1, 1 over 2, and then kind of 1 over n, you get closer and closer to the origin, right? So on this plot, what you want is the one, I guess, is the value at finite n, so it's kind of somewhere very close to the origin. And what you know often is this limit. And if you know that it's, the derivative is bounded, it immediately tells you that these two guys couldn't be too far. Right? This is just, proof by pictures, right? Okay, so quantitatively it says that, if p is kind of not, if p is roughly smaller than root n, then it's kind of good. Okay, so how does it actually work, right? So let's again visit this example with eta IGT. And I guess I didn't choose such a good one because this is not exactly a polynomial, so you have to do some truncation, but temporarily just think this, pretend this is fine, and it will actually be fine. So the part that's really interesting is this series of 1 over n. Right? Suppose you truncate at degree p, you get this 1 over n expansion that a priori seems pretty crazy. Presumably have lots of cancellations and intricate combinatorics. However, using this Markov inequality, it tells you that the sum of this whole thing is bounded by some innocent-looking object. Right? So 2p squared over n times kind of roughly the supremum of f. So there's this truncation error that makes it a little ugly, but will be fine. Okay, so somehow this gives you a bound on how close this finite end expression is from the sort of the asymptotic value, right? So just to check that the proof works, right? So this function is bounded across dimensions because it's average trace of it's a normalized trace of a unitary, and as long as truncation area is pretty small, then this would remain be good. And again, if the truncation degree is you choose it good enough, and actually it would be roughly t, right? If you want e to the IGT, roughly this would be the right scale. And indeed, this is just some fact that moments of Gaussians are low-degree polynomials 1 over n. And here, the only thing we need is that this p is a degree. I don't actually know what this function is. Still today, I don't know what's inside here. Maybe you guys know, but I actually don't know. I only know that it's bounded. The degree is bounded. Okay. And we do know what the asymptotics is. So then all these combined together already give you like a quantitative bounds on the difference between these two. And there's somehow very little work has been done. So any questions? So this is kind of the principle behind this manipulation. Any questions?
Is there a reason you're telling us about exponential rather than an actual polynomial?
Sorry, yeah. So no, this is just like one example that I can write down without writing extra conditions. Yeah. Oh, sorry. This just means a limit, right? So this just means if n is truly infinite, then the first term. Yeah.
It's a characteristic function of a semicircle law.
Yeah.
And what do you do with truncation error? Because it seems, how would you bound it? Because you
Oh,
don't know
right.
anything, right?
Right. So this is something about the Gaussians, because Gaussian, there's very low probability that the norm gets very large. So that's why I started with the assumption that the norm, has some moment bound. So this is like a feature of, if you want to deal with these Gaussians, like so suppose you want to do a similar thing with unitaries, then there would not be this term. Yeah. But then, okay, and then you will see something have to change. So it's roughly like this, and then if you change ensemble, you might tweak, somewhere in this argument. Yeah. But this truncation is really innocent. It's just because the Gaussian is most likely bounded, and that allows you to truncate the Taylor series. Like there's nothing too crazy going on here. But yes, you could really just take like a low-degree polynomial from the start, and it would sort of make this nicer. Okay. So let's do some exercise. So, what's special about the thing I wrote down? Not really that special. Let's look at this guy. I'm sure you guys know how to control this guy, but right. So there's like a trace of u to the p, and then you take sort of some kind of variance of this guy. Well, let's go through the checklist. Right, it's bounded across dimension because it's some kind of normalized trace. It's a rational low degree because you now use Weingarten. There's no truncation because Weingarten is sort of get exactly a low degree polynomial, but now it has some poles in the expansion, right? Well, what that means is that you have to invoke like a rational function version of Markov, and that's sort of all it is. Okay, so there's one example. Another example, suppose you want to calculate these moments for permutations. Again, this is bounded. low degree rational. I guess there's some version of Weingarten for permutation. This seems a bit more complicated, but you can still do it. And the poles are all at the good places. And this was also known. Okay. Make sense? Okay. So now the audience might be complaining that this conference is really about norms, not about moments. So far I've only told you about, in some sense, some better versions of weak convergence. But you may ask, how do I think about the spectral norm problem, right? And is there a way to kind of use the same principle to do it here? And the answer is yes. And this will be the second part of the talk. Okay. So recall, in our setting right now, we only know that Gaussian is most likely bounded in some other, within some bigger range. And now you can ask, is there a simple argument to see that it has to be this number? It has to be 2. Okay. So I guess traditionally, if someone just gives you a generic matrix and you ask about the norm, you try to do like a trace method calculation. Okay. So this is sort of one way you could go about this. Okay. Okay, so let's see how we'll extend this approach to norms. So suppose you want to do this moment method. Usually it's okay if you have fixed n and let, fixed p and let n to be large. That's sort of the weak convergence kind of regime. However, if you want to control norm, you actually need slightly growing moments, and you invoke this nice inequality. But sort of what you're implicitly assuming is that you kind of somewhat know how this 1 over n expansion look like. So heuristically, if this is going to work, it tells you that if you write down 1 over expansion of this property, you somehow need this exponent to be roughly the same, right? If there's like a very high order term where this number is so much bigger, then if you want to apply the trace method, the boundary would just be swallowed by the biggest exponent. Okay. And I guess for Gaussians, if as an afterthought, is actually probably, I think all these guys are pretty nice. But in other examples, such as random graph, this is actually, the high order terms actually are different, has a different exponent, kind of the base than the leading ones. Okay.
Are you saying that they're too large in the random graph?
Yeah. Suppose this is, suppose A2 is different from A0, right? And then if you try to do moment method, then this guy is going to be dominating. And I guess this is the tangle that would happen. Okay. So here's the recipe. So instead of taking this, g to the p, instead you put a test function, and you should imagine this test function is something that looks like, some little bump around somewhere on the spectrum. In particular, if you want to think about this as moments of Gaussian, it's going to have oscillating signs. Yeah, because a polynomial will usually look like this. However, you want to take suitable combinations so that it kind of ends up being bounded. Right? And somehow this is where the magic comes in. So once you take a suitable test function that somehow has low enough degree, effectively, you can plug into this argument. You say, okay, let's look at this guy, expanding the 1 over n series. As long as you somehow know that the first 2 terms are good, right? Suppose if your test function is not in the bulk, and if it's outside, and if you're able to say this is 0, you're so in good shape, right? And there also, how do you deal with all these higher order terms, right? What if they just get really, really big? And what if this is actually bigger than 1 over n squared because this f2 is doing some crazy thing? So somehow the whole point is that these higher order series are actually very, very well behaved. So like this 1 over n expansion is actually really nice. And then we end up getting, so generically you get a bound that looks kind of like this. So in some sense, if your test function kind of has like a window of epsilon, this thing actually ends up being bounded by poly 1 over epsilon divided by n squared. Okay. Right, so if your test function, I guess, ends up, if there's 0 and this thing is bounded by n squared, you actually basically win. It tells you that there's just no basically, on average, very little eigenvalue here. There's less than 1 eigenvalue here.
So H will be typically depend on the model, or?
No, doesn't quite. Yeah.
And does H have height of order 1? It's just supported.
Yeah, sorry. Yeah, height over field of 1. Yeah, that's right.
But you have to know where the edge is. You want it to be supported outside the box. Right?
Yeah. No,
That's all.
this is 2, right? This is 2.
ordinary hope is.
So maybe just, I just want to add that it's not clear a priori that for any test function you will have such a power series expansion, right?
So there's some way,
What you're explaining will yield that, but this is kind of like some heuristic.
Yeah. I guess, in principle, this thing could just go on and on.
Well, moreover, like the expansion itself is kind of ill-defined things because f presumably also depends on n, or I don't know, does not. Like, can you really move terms between the terms of this expansion somehow?
Right. So if f is a polynomial with fixed coefficients, then this does make sense, right? Because for each, g to the p, there is a 1 over n expansion.
Well, kind of what I'm trying to say is suppose that you just are given some n, n equals to 1,000, right? So then you can really write this, then there is some freedom. You can move between one term and another term in your expansion, right? There is no canonical way to say which term actually belongs to what, right?
You're right, but really the starting point is you cannot just look at this object and just say, okay, for each trace g to the p, you replace it with some a polynomial in 1 over n, and that's a fixed polynomial. But you're right, you have to kind of think about what is being fixed. So you should think of this h as being fixed. H is being fixed, and you vary g. Then there's going to be a sort of such expression for every n. And I guess this 1 over n it does have some combinatorial meaning. Like, I guess this is like kind of like genus 1, or, it corresponds to some systematic expansion.
Is there any reason for working this out that you would expect the linear term to be 0 outside the?
Oh, right. So this is an explicit, more like you need additionally understand these. So this is usually just by weak convergence, and this one it could depend on model. Yeah. So this is sort of the extra input that's needed. Yeah. So but it's Gaussian. Somehow for GUE this is just 0, so it's pretty happy. But for other models, this may not be. Yeah, this would depend on the model.
Do you have some easy way to tell when it's going to be 0 other than by working out?
Well, I think there's some way to say. I guess there's some sufficient condition, but I think generally this would just have to do it because at least for this random graph, like random's for this expander kind of setting, it's not a priori easy why this isn't well behaved. Yeah, this is like you have to calculate it.
I guess one canonical example is GOE, right?
Oh, that's true. That's true. Yeah. So you do, so F0 is fine, usually very fine. When this one, you have to look at, have to use a little bit of extra structure. But so the point is that you actually don't need to care what's happening here. You really only need to do this first one, and that somehow is sufficient, because this 1 over n expansion is so nice that all the higher ones is really bounded by 1 over n squared. Cool. So I guess you guys already poke a bit about what's the thing to check, right? So let me just reiterate. So for Markov to work, you need this thing to be bounded, right? So correspond to the constraint that h is a bounded test function. So the whole thing would be very different if instead you choose h that looks like this. That's not good. So here we really want something that's kind of bounded. Okay. And so this low degree is, have to be a bit careful because if you want like really a test function that looks like this, you actually have infinite degree. So then you somehow have to make sense of how fast how fast this could be approximated by a low degree object. So that's you need to do a little more work, but it roughly says that h is kind of smooth and nice and doesn't kind of it kind of have a finite width. And then indeed for this to work, you need to understand the first two terms.
To use Markov in the case when f is a rational function, you need to know something about the poles, right?
Yeah, that's right. That's right. But it just ends up for hard unitaries and for permutations, the poles are at very nice position. They're just very far from zero.
But there could be examples where that's a bottleneck in the proof.
I think in the end, not quite. Yeah, somehow this is not so bad. Yeah. But before we go to proof, it would sound like the rational could be very dangerous, but ends up being not very dangerous. Just somehow the thing that appears not so bad. Yeah. And there's a way to kind of make sure they don't, they end up not being so important. But you do have to kind of be careful about the poles. Yeah. Okay. So I'll use the remaining time to try to give you a sense of how these arguments put together. So one step is to do basically some kind of Taylor expansion and to say that look, all the higher order terms are bounded by something like n squared, 1 over n squared, and let's first do this for low degree test function. So suppose it's really a polynomial. It's not like this bump. It's like just some fixed polynomial. Then again, sort of like this calculus and then Markov give you such a bound, right? It allows you to control the 1 over n expansion to second order, given the function is bounded. Right? So here we're kind of really using the fact that the thing you're trying to do is it's a test function applied to a matrix. So that thing just couldn't be too large. Okay, so no question here. And I guess in principle you could say I want higher, so the better bounds you could go to f2, f3, and this all then you just recall like a higher order Markov, and this is actually can all be done very systematically. But then if you want to do that, you need to sort of know you need a higher order understanding of the spectrum of these f's. Okay, so that's the first step, and then the second step is to understand the first few terms, right? So in this explicit example of GUE, basically what you need to do is to understand this leading order expansion. And the first term is actually quite nice. This is just semicircle, right? So really the only thing you care is this new one, this kind of some kind of 1 over n derivatives of nu in the limit of n is very big. Right? So there's some kind of infinitesimal object. So you would be in good shape if this new one and new zero ends up being kind of the same support. So then there's this new one somehow doesn't produce new outliers kind of outside of the existing spectrum. Yeah, and then in general this is problem dependent. I think for GUE this is nice. For GOE this is not as nice. And you have to and I guess so for GUE, this is exactly 0. For GOE, I think it's not 0, and then you kind of have to know a bit about what it is. Okay. And then if you want to go to higher order, you need to start thinking about higher versions of this, higher order versions of this, which might end up still giving you some combinatorial problem, but at least in this time, like you fix the order and then let n to be infinite. So, okay. Okay. So one extra care needs to be paid when you study an actual test function that's not a polynomial. So if you really want something to look like this, but not some polynomial which might end up blowing up outside, one needs to be slightly more careful about some choice of parameter. Right? So what you really want is that you choose this function such that its expansion into some polynomial basis, in this case is Chebyshev, ends up being a good choice, that you want this coefficient to decay very quickly with the degree. And in this, you somehow interplays very nicely with the quantitative bounds that you end up giving something like this. Right? You basically do the same, do this Markov for each terms, and then you kind of just sum them up, and then you kind of truncate somewhere where the approximation is already just very, very good, such that this term is very tiny. So the extra truncation error is just very tiny. So there are some conditions on how fast this needs to grow, and then so you need to choose like a smooth enough version, like a smooth enough test function to ensure that this guy doesn't go crazy. Okay. Okay. So here's basically the end of my talk. So in summary, I've tried to walk through an example and show you like a recipe to do this random matrix calculation by kind of taking this 1/n expansion very seriously, and so give you some input such that if those conditions holds, then you can believe this 1/n expansion, and you can just look at the first few terms and then sort of conclude the analysis. Okay? So I mean, still, there's something that we don't fully achieve. So for example, we really use so little assumptions that doesn't end up always getting optimal results, right? So for example, is there a way to kind of incorporate this argument with more understanding of the ensemble, right? That's not entirely obvious yet, but I think that would be pretty cool. And then so if you ask the same question in a different way. We try to understand when are these arguments actually optimal, because we use so little assumptions. For example, we didn't really get this optimal results for random graphs. Okay. And for more of a spiritual questions, how so far all these arguments really depends on this existence of 1/n expansion, and this is kind of currently it's only really holds for these nicer. It's called more classic ensembles like GUE, GOE, H-random. Somehow this 1/n was just given to us. But if you have a different ensemble that is not exactly those nice ensembles, is there a way to make similar arguments work? It's also an interesting question. So I will just stop here and thanks for